Welcome back to another video. In today's video, we're going to be looking at dot and cross diagrams. We're going to be drawing the dot and cross diagrams for covalent bonding. We did a video where we highlighted the dot and cross diagrams for ionic bonding, and in today's video, we're going to be looking at the drawing dot and cross diagrams for covalent bonding. So that's the objective of today's video. And if you haven't subscribed, don't forget to like, share, subscribe, share the video as well. And also remember that you can get a free worksheet, right? The link is in the description. And you can also get customized study guides and stuff like that. So let's go. Now, as it relates to covalent bonding, right? Covalent bonding, this is when non-metals, right? And it's important that you know the periodic table, right? So if you don't know the periodic table, you're gonna be having a problem. So first of all, you have to ensure that you know the periodic table. So previous knowledge. So that's how it works. You're going to use previous knowledge, right, to help you pass the subject. Now, as it relates to covalent bonding, quick definition. So this is non-metal, right? Non-metals are sharing electrons to get full outer shell. And we know that non-metals, we can find non-metals on the right side of the periodic table. We have that group, we have groups 5, 6, right? 7. Those are non-metals. So you have those groups are non-metals 4, right? So what happens in covalent bonding is that they want to basically obtain the same objective, and the objective would be to get a full outer shell. You have the first shell can hold 2, the second shell 8, right? The third shell 8, right? As you move on to higher levels, right, you will see where books talk about 18 and so on. So if you move on to study chemistry at higher levels, then you will see some books talking about 18, but at the CXC level from grades 7 to 11, right, you only need to know this. So it's 2, 8, and 8. The first shell can hold a maximum of 2. The second shell can hold a maximum of 8. And the third shell, 8 as well. Now, the idea why the non-metals in covalent bonding share electrons is that they want to obtain a full outer shell. So depending on their atomic number, right, the main objective, they want to have a full outer shell. Now, the examples that we're going to be doing today, we're going to be doing water, we're going to be doing oxygen, we're going to be doing nitrogen. So these are the examples that we're going to be covering today. The idea is that you also want to know the formula as well, and we're going to be doing some videos highlighting how we write chemical formulae for compounds. So we're going to show you the dot and cross diagrams for bonding in water. Now, as I mentioned before, covalent bonding is when non-metals share electrons. Both elements, right, they want to have a full outer shell. Now, and again, the atomic number is important. The atomic number and mass number is important. So the atomic and the mass number for hydrogen is 1 and 1. Once you're watching this video, you should have a periodic table in front of you so you can follow. And then as it relates to oxygen, the mass number is 16 and 8. So we're going to show the dot and cross, and in my previous video, right, the link is at the top to watch that video. We mentioned that in dot and cross diagrams, you're only showing what's on the valence shell, and the valence refers to outer. Now, you have what we deem as cross and what we'll deem as dot, to show that we write it properly. So this would be what we deem as a cross, and this would be deemed as what we call a dot. So we're going to use 1 to represent the electrons, right, and what's taking place in covalent bonding. Now, as you can see right here, we have 2 hydrogens bonding with 1 oxygen. That's the formula for water. So you have H2O. Now, in bonding, right? So let's write the EC. And I mentioned the EC. The EC for oxygen is 2, 6. And that therefore means on the valence shell, we have 6 electrons for oxygen. As it relates to hydrogen, the EC is 1, and that therefore means the valence electrons, or the valence electron on oxygen on hydrogen, is 1. Now, this needs, remember the second shell can hold a maximum of 8, right? And the first shell can hold a maximum of 2, as mentioned earlier in the previous slide. Now, in bonding, right, they're going to share electrons to obtain a full outer shell. So this hydrogen needs additional 1, right? To have a full outer shell, this oxygen, needs additional 2 to have a full outer shell. So during bonding, what you do, right, you're going to, as I mentioned before, you start out single. So I'm going to use a dot to represent the electrons in hydrogen. So I start off single first, then I'm going to start the pair. So it's 2, 4. Let's get rid of 1. So it's 2, 4, and 6. So we have 6 on the outer shell of oxygen, right? We have 6 on the outer shell of oxygen. So I want to let it clear as possible. So let's just put 1 at the bottom, right? Just put that 1 on the bottom. So it's 2, 4, 6. So we have 6 on the outer shell of hydrogens. So what's gonna happen now in covalent bonding, you're gonna have both hydrogen and oxygen sharing electrons. So the idea is that they're putting forward an electron to obtain the same objective. So in covalent bonding, hydrogen and oxygen, right, they put forward an electron here. So you have 1 from oxygen here, 1 from oxygen here. Both have a full outer shell now. So 1, 2, right, they're sharing 1, 2, 1, 2. So this belongs to oxygen as well, and this. So in this side, both of them are sharing electrons. So you have this one comes from hydrogen, this one is from oxygen, this one is from oxygen, this one is from hydrogen. So if we count the amount that oxygen has now, so it's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 on the outer shell now of oxygen, and then you have 1, 2, 2 on the outer shell of hydrogen. So they both have a full outer shell now. In some books, you will see them drawing it like a Venn diagram, right? So something looking like this, you draw it like a Venn diagram, right? They're sharing electrons to ensure that it's drawn as clear as possible. And as I'm drawing it, don't forget to like, share, and subscribe, right? We're trying our best to do videos on all the topics that people are asking us to do. So don't forget to like, share, subscribe. That's the least you can do. Alright, so in some books, as I said before, you'll see them drawing it like this. So you have this one representing, so you put that one representing oxygen, right? And then remember you have that one from hydrogen, that one from oxygen, that one from oxygen. Then I write the element symbol for the element in the middle. So in some books you'll see it having like looking like this. Now before we move on to oxygen molecules, right, so for those that are not participating in bonding, we refer to them as being lone pairs. So lone pairs, these are electrons that do not take place in bonding, so we call them lone pairs. They're loners, right? So they're called lone pairs, that therefore mean they don't take place in bonding. So you can write that down. Don't take place in bonding. Let me just put it beside it, sticky note. And then of course, the one that are taking place in the bonding, like this one, it'd be bond pairs. They take place in bonding. So in this case, you'd see you have a lone pair here, right? And then you also have one up top. So if I should combine it and say, all right, these are the lone pairs. So they, as I said before, they are not taking place in bonding. These are the bond pairs. Now, another important thing that you also need to take note of, right, in terms of the type of bond. When you move on to organic chemistry and so on, you have an understanding when it's a pair of electrons bonding, it's a single bond. When it's a pair of electrons bonding, it's a single bond. When I move on to oxygen, I will draw the double bond. So when a pair of electrons is bonding, right, it is called a single bond. And we normally use a dash to represent single bond. So in this case, you will draw what's the bond forming between hydrogen and oxygen would be something looking like this, right? Because as you have a pair of electrons bonding right here, just one pair, right? If both put forward more than one electrons, right? You'd have if you have two pairs coming from one of the elements, right, one of the atom, then you would have double bond. But I will explain that further in the next part. So this is the covalent bond for water. So let's move on to the next page for oxygen. They exist as what we deem as diatomic. So you have O2. So what's gonna happen now in oxygen? Remember, as I mentioned previously, that the EC for one oxygen atom, right, is for oxygen atom is 2,6. It's 2,6, right? So you're gonna have two oxygen combined together to obtain the same objective. Right, so I'm using this diagram. So I'll start out single first. So what's gonna happen, each oxygen is gonna put forward a pair, right? A pair is gonna come from each oxygen. To prevent confusion, remember I'm using dot for one, I'm using cross for the other. That's why we call it dot and cross. So in this case, each oxygen is putting forward a pair, right? And this is what they're bonding. This one coming from this one coming from this one. So let's count it now. Remember, as I mentioned previously, you can draw the Venn diagram. So there is like their outer shells are overlapping, right? So you have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So each is putting forward. So you have one pair electron a bond here, another one a bond here as well. So as remember as I mentioned before, when you have a pair bonding, right, you form a single bond. But in this case, you have two pairs bonding. So you're gonna have what we call double bond. You use 2 dash to represent the double bond. So oxygen molecule contains a double bond, and the double bond comes from these two pairs. A single bond here, a single bond here, two single bonds form double bonds. What else? Lone pairs, as I mentioned. So this is the covalent dot and cross diagram. This is a lone pair. 2, 4, 6, 8. So this is the lone pair. What else? So this is as I mentioned before, this is the double bond between the oxygen atoms, right? They exist as diatomic. They want to obtain the same objectives of getting the full outer shell. So they have a full outer shell, and as I mentioned, the second shell can hold a maximum of 8. So this is the covalent bond for oxygen molecule. So we're going to move on now to nitrogen, which would be the last part of this lesson. All right, so this is what we're going to do. We're going to be looking at nitrogen now. So we're going to be looking at nitrogen now. So let's go. The atomic number, the mass number is important. So for nitrogen is 14 and 7. And the EC, which represents the electronic configuration, 2 and 5. Now each oxygen atom needs additional 3. It needs additional 3 to have a full outer shell, because remember that the second shell can hold a maximum of 8. So this is how you draw the bonding, the covalent bond in nitrogen molecule. So two nitrogen atoms are bonding, 5 on they have 5 on the outer shell. So each is gonna put forward 3 electrons, and in essence you're gonna have 3 pair of electrons bonding. Remember, as I said before, when a pair bond, you're gonna have a single bond. So in this case, you're gonna have a triple bond forming. So 3 single bonds combined together to give you a triple bond. So let's put that for one cross for the other. 1, 2. So let's count 1, 2, 3, 4, 5, 6, 7, 8. So you have a triple bond forming. So this is a simple covalent bond for nitrogen molecule. So you have a triple bond right there. Here, 1, 2, 3. And this is the simple, these are how you draw the simple diagrams for additional ones that you can practice as well. So if you have made it to the end of the video, you can practice these. F2, carbon dioxide, CO2, and you have others as well. Right, so remember that on cross diagrams, right? These for covalent bond. So you have non-metals share electrons to get full outer shell, right? And then you have, as I said before, they have the valence electrons, right? And then at this level it's 288. And we did the example of water, oxygen, and nitrogen. And then remember, you have lone pairs. Lone pairs, these are what we deemed as those that are not taking place in bonding. And then you have, this is water. Don't forget that the periodic table is also important in drawing the dot and cross diagrams for ionic and also covalent bonding. So the idea is that if you're going to become a great student in chemistry, you need to know your periodic table because it's important. Just like how you have a block that builds a house, right? And it's the foundation. You have the periodic table. It's the foundation for chemistry. But that's for water. And then for the next one for oxygen molecule, right? That's that. And then for the nitrogen molecule, that's that. You can practice these. If you have made it to the end of the video, don't forget to like, share, and subscribe. And feel free to reach out to us for customized worksheets, private tutors. If you also want to be a part of our Google Classroom, the link will be in the description. Don't forget to like, share, subscribe, and also spread the word as well. Until next time, peace.